Sairam, having seen an introductory part of coordination compounds and a theory about Werner's where he explained about primary and secondary valences, now let us concentrate on the important terms that come in this chapter. Because since this being an altogether new concept, we first need to understand and analyze what are the terminologies that come in this chapter. So, let us see the first one now then. It is coordination entity. Now, what do you mean by entity as such? It is nothing but a segment which is under consideration. So, here in terms of coordination compounds, it is nothing but a central metal atom which is there and which is combined with various ligands or those who are donating lone pair of electrons. So, in the first example, cobalt is the central metal one, the Cl3 and NH3 thrice are the ions or molecules which are donating a lone pair of electrons. Similarly, nickel is the central metal ion, the carbonyl group CO is the one which is donating lone pair of electrons. Then what is the central metal ion? We have been using this word a lot of times. So, that is the one which is present at the center which can attract all other electron pairs, and because of the arrangement that it forms, it can give perfect geometrical arrangements like tetrahedral, octahedral, square planar, all those parts. So, again in that example, nickel and carbonyl can be seen in combination and nickel is the central metal ion. Now, what are ligands? This is the word that we have come across many a times now. Ligands are something which can donate a pair of electrons to this system of central metal ion. And how do they donate? It is by a property called as coordinate bonding. Now, for example, in a case where if I have a coordination compound of PtCl6. Now, what does this ligand here indicate is that, see, we already know that chlorine atomic number is 17, the configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Now, these 3p5 systems and all are there, these are all internal systems, so they will not take part in bonding. This is something that we have studied many a times. These 7 electrons are the people who are present outside, and when I consider it as a negative ion, what happens is negative indicates excess, which means that there is another electron which is present with this. Along with the 7, there is another one. So, these 2 electrons will tend to form like a coordinate bond. So, when I write the structure, actually I am going to show it up like this: Pt, all this Cl which is present here, and the coordinate bonds I am going to show like this. Now, what does this arrow mark mean is that this Cl outside it has 7 electrons, of that 6 electrons I will write it as lone pairs. The 7th electron and the additional electron, because it is a negatively charged species, those two will act like a electron donating system, and whoever donates a lone pair of electrons, them we call them as ligands. This is the terminology used for people who donate lone pair of electrons. So, that is what we see in the statement there, that whoever donates these lone pair of electrons can be called as the ligands. And in this we have unidentate, bidentate, tridentate, tetradentate, and normally above didentate we call them as polydentate ligands. So, what is unidentate ligands? Suppose a system is there, say for example Cl minus. I already told that Cl will have 3 pairs of lone pair of electrons and 1 electron which is outside, the 7th electron and this excess electron, these two will act as a donating system. So, because one Cl can give just 1 lone pair of electrons, it is called as unidentate. What about bidentate then? We have an example like this. So, CH2, CH2, NH2, NH2. Now, what is the name of this? How will you name this? Actually, if you see, CH2, CH2 can be called as eth system. So, I can name this as ethylene diamine. This is how I can name this, ethylene diamine, because 2 amine groups are there. Now, this compound which is there, CH2, CH2 is as it is. We know that lone pair of electrons do not take part in bonding. So, these can actually act like an electron donor system. So, for this molecule, this is one part which can donate electron, this is another part which can donate electron. So, one molecule has 2 centers of donation, and therefore, this I can call it as didentate ligands. So, what are these didentate ligands? Those which can give you 2 lone pair of electrons. So, in this didentate ligands, remember that they are present at different centers. One confusion that you can come across is you actually have 3 lone pairs here, then do they not donate electrons? So, basically one atom which is there for the coordination bond can donate 1 pair of electrons. See, it may have multiple pairs, but donation will be 1 pair of electrons. In this also, this nitrogen is donating 1 pair, this nitrogen is donating 1 pair, but because it is an entire molecule, when I consider it on the basis of molecule, I will consider that 2 lone pairs have come out of it. So, this is what is the didentate ligand. Then let us see about the polydentate ligand now. So, what is polydentate ligand? Naturally, those which can donate more than 2 can be called as polydentate ligand. So, as an example, we see there a compound named as EDTA. So, what is this EDTA? It is ethylene diamine tetraacetate systems. So, what has happened here is once it is polydentate, it indicates that there are more number of electrons which are available for donation. So, this is the structure of polydentate ligand EDTA. So, what is this EDTA? If you see in that formula, they had written it as EDTA 4 minus. What is that 4 minus? Ethylene diamine, because 2 nitrogens are there, tetraacetate. See, CH3COH is acetic acid. We know this from the organic chemistry. So, the hydrogen has gone out as H plus and negative charges are remaining here. So, tetraacetate, each one gives a lone pair of electron for bonding. Along with this, the lone pairs that are present on nitrogen also gives for bonding. So, which is this? This is called as hexadentate ligand. Though we classify it under polydentate, this is hexadentate because 1, 2, 3, 4, 5, 6. 6 different centers are available for donation. So, these are called as ligands, and depending on the number of centers, we can term them as unidentate, didentate and polydentate ligands. So, this is about the study of ligands which are present. We have another one type of ligand which is called as ambidentate ligand. So, what is this ambidentate ligand? We saw that ligand is that compound which can donate a pair of electrons, but for this ambidentate ligand they have one speciality where the molecular formula in both of this is same, NO2 and ONO. Here nitrogen is the one which donates a lone pair of electron, whereas here oxygen is the one which donates the lone pair of electron. So, this is called as ambidentate, same molecular formula, but the person who donates the lone pair of electron differs. And how does it differ? You cannot guarantee which one differs. So, it depends on the structure of the compound which is there. So, ambidentate, amphoteric, these type of terminologies you have come across. Ambidentate is something where same molecular formula, but the person who donate electrons differs. So, this is about the ambidentate ligands which are present in this case. So, moving on to further terminologies in this parts here. So, let us see the next one, that is coordination number. Coordination number is nothing but the total number of ligands that are attached. So, as an example, you are able to see there PtCl6 2 minus. So, how that 2 minus charge came, that we will come to know when we discuss the nomenclature. But for now, what we shall see is what is coordination number. This platinum which is there is coordinated with 6 chlorine atoms, and therefore, I can call this as the coordination number being 6. But if you see the second example, FeC2O4. Now, this FeC2O4 which is there is actually bonded in just 3 numbers. So, if you write the formula, you are just able to see it as FeC2O4 3 times. So, just 3 times it has been seen. But the coordination number, if you see in that part once again, you will see that the coordination number is written as 6. Now, why it is written as 6 is because C2O4 is a didentate ligand. So, the C2O4 structure, when we tend to write, it is like this, that is called as oxalate ion. And from one molecule you are able to see 2 donation centers, always negative charge or excess systems. So, because 2 donation centers are there, we are able to donate the electrons from that. And iron, from one C2O4 it is able to get 2 pairs of electrons. So, how many it will get from 3? You will naturally get 6. So, the number of lone pair electrons attached to the central metal ion determines the coordination number of the compounds. So, this is about the coordination number. Now, let us go to the next one, which is there, which is present coordination sphere. Sphere, what is the sphere? Sphere is something which will have an enclosed area. Generally, we term it like a circular part, but what we mean here in this coordination part is, the coordination sphere is that part of a system where you cannot ionize those compounds any further. So, in the example that they have given for you, the compound has potassium, iron and cyanide ions present in them. So, when this is present here in these cyanide ions, when it splits up, you will see that in this part, once the splitting takes place, you will see that it splits up into 4K FeCN 6 4 minus. This is how the splitting takes place. So, this part is called as coordination sphere. This is called as counter ion. What is the role of a counter ion? We have seen that if there is a negative charge, if you want to stabilize it, you will have a positive charge. Suppose NaCl, you have Cl minus ion. If you want to stabilize, get Na plus. If you have Na plus, get Cl minus. So, here the role of this ion is just to act like a counter ion. This is called as coordination sphere, in which it is enclosed. So, moving on further regarding the terminologies that we have, the next one that we have is coordination polyhedron. This is nothing but how it is spatially arranged in the system. This depends on the type of bonding that it takes place, the number of ligands that are attached to the central metal ion, and how the spacing takes place in those compounds. That can only be generalized once we study the various theories like valence bond theory and crystal field theory that we tend to come across these. So, some types of polyhedron, they have shown there octahedral, which means that there are in total 6 ligands which have been present, and if we have to understand about the ligand systems which are there, the octahedral structure is nothing but, supposing if we take this part here, if this is considered as a plane of a system, I believe that the central metal ion is here at the center, the 4 ligands are present at the 4 corners. The 5th ligand is at the top, the 6th ligand is at the bottom. So, what is octahedral is in total 6. Now, why that word oct comes then? Because it is 8. Oct comes because this 8 system which is there, in these 8 numbered systems, the faces are 8, but in total the ligands are 6. Tetrahedral, we have already seen in the structure of methane, square planar, trigonal bipyramidal, square pyramidal. These are various types of polyhedrons that can be obtained in coordination compounds. Similarly, what is the oxidation number? Now, this can be determined by the total number of ions that have been present in these cases. We know very well that S block and P block have a definite oxidation number, but D block have variable oxidation number. And we have already seen in the introductory part that D block elements form these coordination compounds very significantly. So, as an example, they have given you copper cyanide 3 minus charge to get +1 charge. So, why does it hold a +1 charge is because the cyanide ion, we know the charge to be as -1. So, all this need to be known beforehand. So, here this is -1. What is the total negative charge available here is -4. What is the overall negative charge of the compound is given at the top, -3. So, if this is -4 and this is -3, the charge on copper will have to be +1. This is how we get by calculation. So, we know that copper can have +1 as well as +2 state. So, in this case it is at +1. Let us similarly calculate for this also. Potassium, we know it to be +1. This is an S block element which has a perfect structure as such. So, therefore, if I can calculate it, it will be 4 into +1 plus iron, I do not know because it is a variable oxidation state. Then Cn, there are in total 6 and we know that the charge on Cn is minus, and this compound entirely does not has charge like the way this compound had. So, that is why overall I am keeping it as 0. So, I can write it as 4 plus x minus 6 is equal to 0. You calculate this, you get x is equal to +2, which means that the oxidation number of iron in this compound is +2. So, the oxidation number calculation is exactly similar like the way you did for the normal salts. Now moving on from this part, we have homoleptic and heteroleptic complex. We have come across this word homo, hetero. Homo generally means one single type, hetero means multiple types. So those compounds which will have only one type of ligand, that we can call it as homoleptic ligands. Those compounds which have more than one type of ligands, we can call them as heteroleptic. So in example, you can see that the first example having cobalt and amine, amine is the only type of ligand that is present in that example. But in the second example, if you go through, you will see that along with the amine there is also chlorine present. So if more than one type of ligands are seen, we call them as heteroleptic. If only one type of ligand is seen, we call them as homoleptic. So this is all about the terminologies that are present in this chapter, which you will come across all through, where with this basics you can very easily understand the further concepts that are been present in this. Thank you. Sai Ram.